Hi, my name is Joyce and I'm going to be a junior in the Materials Science and Engineering department. Today I'll be going over some of the work I've done as a SURE participant on fluoride catalyzed rearrangement reactions of polyphenylsilsesquioxanes with Professor Richard Lee. So first off, I'll give some background on what silsesquioxanes even are, and then I'll talk about some of the work I'm doing with polyphenylsilsesquioxanes, some of our results, and finally, applications of this research. Why are we even doing this in the first place? To begin with, silsesquioxanes are a family of molecules made up of silicon-oxygen cores. What's so special about these molecules is their perfect symmetry and small nanometer size. So in general, our research group wants to control the placement of these functional groups, which are shown as R on this picture. We want to change these groups so that we can get many different properties, because we know on the nanometer size scale, by changing the R or functional groups, we can get many new and exciting materials. What I'm specifically working with is this molecule known as polyphenylsilsesquioxane. I run rearrangement reactions with this PPS, and when we add tetrabutyl ammonium fluoride, which is the thing shown here, we in particular want to isolate the decaform of this molecule. This reaction is particularly relevant because our starting material is very cheap and relatively abundant because it's a byproduct of another reaction. We can remove the fluoride ion that happens by adding calcium chloride, and then we further purify these cages, the decaform from the octa and dodeca, by precipitating the mixture into methanol, cyclohexane extractions. And we can also filter out the fluorine atom, which is here, adding calcium chloride, which will then remove the fluoride ion from the cage. So eventually, once we purify the decaform, or the T10 form of it, we can run further modification reactions of these decasilsesquioxanes. Examples of the decasilsesquioxanes are shown here, as we can get an example of it. Here shows a nitration modifications of octaphenylsilsesquioxanes, and we can do such similar things, hopefully, with decasilsesquioxanes. So finally, to go over some applications of this research, we want to isolate the decaform because of the many properties we can potentially obtain. Such properties would include its high solubility and high heat resistance. These properties would make it ideal for solar energy collection and harvesting antenna molecules and photovoltaic applications. So there are many exciting renewable energy-related applications of such research. So finally, again, I'd like to thank the SURE for giving me this opportunity, as well as my professor, Richard Lee.